Okay, so in this lecture, I'll be discussing what we'll call classical limit. This is still work somewhat in progress. Alok. So the idea here is that we will try to use the results that we have gotten so far to see if we can say something about scattering or gravity wave emission in classical scattering. So you will be considering, in general, extreme classical scattering. Okay, take for example, suppose you have two black holes, okay, which are coming at relativistic speed, okay, which scatter from each other, coming at a distance of the order of the Schwarzschild radius, okay, and goes far away. And the spirit of soft theorem is that by knowing the initial trajectory of the black hole and the final trajectory of the black hole, okay, which are the states of the black hole initially and finally, we should be able to say something about the soft gravitational radiation that is emitted during this process. And in this particular example, the soft gravitational radiation means that the radiation should have wavelength that is large compared to the typical length scale of the problem, which in this case will be, say, of the order of the Schwarzschild radius of the two black holes. Okay, because we are taking the distance of the impact parameter to be also of the order of the Schwarzschild radius. So that's the typical length scale. And the question is, can we say something about processes like this, the gravity waves emitted from processes like this, based on what we have learned in soft theorem? Okay, so that's the kind of question we will try to address. But let me begin with the formula that we have derived, okay, and try to proceed slowly from there. So let's take the case of a single soft graviton emission, leading order. Okay, that's a simple case. Leading. And here we have seen that the amplitude for this process is given by the soft factor, okay, times gamma. Okay, so this will be the amplitude without soft graviton. Amplitude without soft graviton. And this, let me remind you again, is you sum over all external states that take part in the scattering. So this means that if you want to calculate the probability of emission of a soft graviton, let's say we are asking about not S matrix but directly probability of emission of a soft graviton with the following properties. Okay, first we have polarization epsilon. Then we have energy between, say, omega and omega times 1 plus delta. Okay, this delta is some small number. And say solid angle omega. Okay, again this is a small number. around some unit vector n. Okay, let's try to calculate the probability of emission of a soft graviton with this property. Okay. So let me remind you again that this is small, and then this is also small. So for this process, the K, the momentum vector of the soft graviton, we have chosen the convention. I have been drawing the diagram such that the momentum is always ingoing. Okay. So in that convention, here you are talking about the emission of soft graviton. So K is actually negative. So it's minus omega 1 and n hat. Okay, this is the direction. This is the energy. Okay, but minus sign simply means that it's outgoing instead of ingoing. So this is a reflection of the fact that we are talking about the outgoing soft graviton. Okay, so the probability of this is not hard to evaluate. I'll write this as is proportional to gamma squared times A. Okay, I'll write what A is. So A will have a piece that comes from the square of the S matrix. Okay, so I have to take the mod square of this. I have already included the mod gamma square explicitly. So A will have a contribution that's mod S0 square. And then there will be phase space factor. Okay, so there is a standard 1 over 2 energy, 2 omega. And then we have the phase space factor. If you remember, it's d minus 1k. But this I can now write, given the attributes that I have here, this can be translated, okay, by 2 pi to the d minus 1. I should have written that. So this can be written as omega to the power d minus 2 times omega times delta and omega. In 4 dimensions, 4 space-time dimensions, this is like E square dE. Omega times delta is the width in the energy space. So this is like E square dE, that's the phase space integral. And we have to multiply by the angular, the solid angle, how much solid angle we are projecting, that's this omega. Is this clear? Okay, so let's put these factors together. This is altogether 1 over 2 to the d. 2 to the d minus 1 and 2, then pi to the d minus 1 mod S0 square and omega to the d minus, this omega cancels with that omega, so omega to the d minus 2 delta and then omega. Okay, other questions? Pardon? We'll see. We'll see why. Okay. Omega is the angular scale. Right? Small omega. Yeah. So omega is small, but this is a delta fraction of omega. That's what. That's how we are measuring. Otherwise, I have to write it as d omega. I'm just writing this omega times. Okay. So now suppose we ask the same question, but for n soft gravitons, m soft gravitons. Okay. Yes, omega is small and delta is small. Okay, delta is small but finite. You can think of delta as small but finite. We are just trying to take a small range. Okay, but it's small compared. This range you will take small compared to omega. But delta will think of the more as a small but finite number. Okay, now suppose you want to ask the probability of emitting m soft gravitons. In the same range. So in this case, the S matrix, the corresponding S matrix will be a product of these S zeros, but because you are taking them in the same range, okay, they are all the same S zeros. Okay, because all the soft gravitons that you are looking for are all within the same cone. Okay, so the same S0. So we get, instead of S0 square, it will be mod S0 to the power 2m. Okay, there are m factors of S0. Okay. And then for each of the external of the soft gravitons that are emitted, we have to include a phase space factor, right? Because each has its independent phase space. So this factor, the rest of the factors will also get raised to mth power. But then of course you have to remember that you have to symmetrize, right? Because you have to, there is a commutatorial factor, okay, they are all identical particles. So the probability here will be mod gamma square times the same factor a to the power m over m factorial. This is clear because there are m of the soft graviton, so we raise it to the power to mth power, and then because they are identical particles, you have to symmetrize. That's this factor of m factorial. Now let's suppose we don't know it yet, okay, but let's suppose that m is very large. Okay, we'll typical m that we'll find in a classical scattering, that is true, right? When two big objects scatter, right? You don't emit one graviton, you emit typically multiple gravitons. Okay, it's classical radiation. But let's suppose that m is large. We will see later under what condition it becomes large. Then we can ask, what is the expected value of m? Okay, at what value of m does this probability distribution peak? Is that clear? So this peaks at del m of log of this number equal to 0. Okay, I have just taken log. You can maximize the a to the m over m factorial as well, but this is simpler. And again, as I said, assuming that the value of m will turn out to be large, we can use Stirling's formula to carry out this expansion. So this log here is m log a minus m log m plus m. Okay, and you can easily check that the solution to this equation is m equal to a. Yes. No, fixed polarization, yes. Because the same polarization, that's why they are identical, right? We are asking for multiple soft gravitons with the same quantum numbers, right, in the same bin, right? That's why you have to put a 1 over m factorial. So if there are two different polarizations, then you'll have a 1 over m1 factorial for the first one, 1 over m2 factorial for the other one, right? And then you have to extreme with respect to m1 and m2. Is same, exactly. Okay, because you have fixed all of them to carry polarization epsilon. No, even in one particular small region, because each of the soft gravitons were restricting to that small region, right? So that's why they are identical particles. Exchanging them will give the same, will be the same configuration. Okay, is this point clear? That so solution is m equal to a. Okay, but we can say so this means that m is large if a is large. If a is large. A, yes, but these, as I said, these you have to think of a small but finite number. Okay, you could also raise the objection that omega is small, right? So how can A be large? Okay, we'll see how to make A large, right? We'll keep omega small, but at the same time, to make it a classical scattering, you have to make the masses of the external states to be very large, right? That's how we are going to make A large. Okay, but right now we are just making the observation that if A is large, then this analysis makes sense, right? Otherwise, of course, it doesn't make sense to extremize, right, if m is 1 or 2. Well, A I think is a dimensionless number. If you, here of course I am calculating everything with respect in the Planck mass, right, in the Planck scale. So A is actually large as a number, right, 1000, 1 million, right. So okay, how large you will see. So what now, okay, that comes in the next point, okay, that you can also see that the second derivative, okay, if you take the second derivative of the same thing, that goes as 1 over m, okay, so m equal to a, that's 1 over a. So this means that the width of the peak, right, so this is large, of course this doesn't mean that it's all that it's finite only at that part, m equal to a and 0 everywhere else, but it's a sharply peaked distribution. The width of the distribution is root m, right, because the second derivative goes as 1 over m. So this should be familiar from various statistical mechanics. So this is the, so width of the distribution is root m, okay. So the expected value of m is a, okay, which is a large number, and the width is root a, right, which is a much smaller number, okay, and that's the sense in which it's sharply peaked, okay. The width is small compared to the actual value of m at which the peak is reached. Okay. So this is what one means by classical limit, right, in the class, that even though the whole system is quantum mechanical, okay, the actual observation, okay, gets peaked around certain classical values, okay. The probability distribution is peaked around certain values and it falls off rapidly as you go away from the central value, okay. That's the way you normally reach classical limit, and here you see this explicitly, how that happens. I still have to tell you how to make A large, okay, but if A is large, then this is what happens. Is this point clear? Okay, now I can also add something else here, okay, that when two large objects scatter, right, of course it's very unlikely that it will only emit soft gravitons in a certain bin and nowhere else, okay, it is going to emit soft gravitons everywhere, right, but you just divide it into bins, okay, and we calculate the probability distribution for a given set of bins. So even if it emits soft gravitons in other bins, right, that will, what it will do is that it will multiply this, okay, by some other factors, okay. Suppose m prime soft gravitons in another bin, okay, it will multiply by corresponding a prime to the power m prime over m prime factorial, okay, and so on, okay. But you can extremize with respect to each of these m's and m primes independently, okay. So the extremization with respect to m is not affected by the fact that the actual scattering process will emit soft gravitons in various bins. Okay. The part that depends on m is always this, okay, and that's what we are extremizing, okay. So this is robust, okay. Even though I have derived this assuming as if you only emit these soft gravitons in this bin and nothing else, okay, that's certainly not a necessary assumption, okay. It can emit soft gravitons in all bins. Okay, are there questions on this? Yes, suppose you ask the question instead of this, that what is the probability that there will be m soft gravitons in this particular bin and maybe another m prime soft gravitons around some other vector n prime, okay, around some other unit vector n prime, okay, or maybe you also change your delta prime and omega prime. Yeah, mod gamma square factor of course is there because you can see the soft factor multiplies, right? It's a product of soft factors, right? So it will always be raised to that soft part, okay? It will be s naught to the power m and then some s naught prime to the power m prime, and so they will just be independently distributed. So the fact that the m is peaked at A, that is not affected by any other emission in other bins. Okay, all that will change. Either instead of having mod gamma square, you will also have some other factors which are m independent, but which may depend on m prime and m double prime and so on. Okay, what to specify. So in each bin, you can independently extremize, and you can arrive at this formula for the expected number of soft graviton emission in a given bin. Well, because of this peculiar form of this formula, that it's a product of the S0s, right? That's why the final probability will be the mod square of each soft factor, right? That's why it's completely uncorrelated. Yeah, but we will see that the M piece drops out in the classical limit. Okay, so it will also be true in the subleading piece, but yes. So a priori it doesn't work for subleading piece, okay? But we will see that in appropriate limit, that problem will go away. Yes. Well, I said proportional to, right? You have to always normalize. Okay, so this is just proportional to this, and that's good enough for calculating the expectation value of M. Yes, that's right. If you do, I mean, and there is a good reason for it. Okay, why this product's formula will break down eventually, right? If you don't go to the classical limit, then certainly, we have seen at the subleading order, right? There is M, okay, whose physically this captures the possibility that there is a correction to the soft factor from the soft particle emission itself. So these are not independent. Then these different soft emissions are not independent events, right? But in appropriate limit, we will see that these become independent events. Okay, so A has to be large. We will see under what condition, but let me write down another formula, that we can also ask the total energy radiated in this bin, total energy in this bin is just A times omega. Okay, A is the number, you just multiply it by the energy that is carried by each soft graviton, so that's A times omega, and all that it does is it puts a factor of omega here, so it's omega to the d minus 1. Okay, so now let's try to estimate under what condition A is large. Okay, and for this let's just consider a specific configuration. Okay, although it's not necessary to consider, have this particular configuration. So let's suppose that the moment of the external lines. Okay, that suppose that all the external objects, okay, which are involved in the scattering, okay, which you can take for example the black holes, they are all of the same, of the order of the masses of the objects, and we will take all the masses to be of the same order. Okay, so black hole scattering, black holes have the same order of masses. Now in d dimension, okay, the Schwarzschild radius Yeah, V over C is of order 1. Exactly, it's a relativistic scattering, right? Black holes are coming at relativistic speed and getting scattered from each other. M is the rest mass, right? So if V is of order 1, right, then momentum is of order M, right? Because gamma factor. But so assuming that the gamma is neither very large nor very small, right? It can be very large. Then you have to think of it as the massless particles, right? So M typically you can think of as the order of the external momenta. Okay. If the things are massive, right? Let's take that to be relativistic, like V of order 1, but not very close to 1, say. If V is very close to 1, you just think of it as the massless particles. Then M, you have to replace M by the corresponding energies. Right? So that's the way we are thinking about this. Okay, so in d-dimension, the Schwarzschild radius of this goes as M to the power 1 over d minus 3. Okay, so d equal to 4a goes as M, right? That's the standard formula, but in general, this is the case. So then we can take omega, okay, which is of the same order as k, of course, as some tau times m to the power minus, let's say tau times A inverse, okay, because A inverse now is the typical length scale of the problem, okay, which is like tau times m to the power minus 1 over d minus 3, and tau is small. This is the soft limit, tau small. Okay, so this corresponds to the soft limit. Tau is some parameter which has to be kept small, because soft means small momentum, right? Small omega. Okay. The typical length scale here is this, the Schwarzschild inverse Schwarzschild, the Schwarzschild radius. So typical frequency is the inverse of that. So you are trying to keep the frequency small compared to that. That's why it's tau times this. Okay, so that's tau is the soft expansion parameter. That's right. Yeah. Okay, now we can estimate A. You see S0, let's look at S0 formula again, right? S0 is sum over I, Pi dot k inverse epsilon mu nu, Pi mu. Okay. So this, you can see this has two powers of m in the numerator, one power in the denominator, so that's m, and then the one power of k in the denominator, that makes it k goes as tau times this, so m tau inverse and m to the power 1 over d minus 3. Did I do it correctly? Yeah, I think that's the structure. Okay, so after, now you have to put the formula for A is here, right? So after putting this formula, we claim that A basically goes as m squared omega to the power d minus 4 basically, because you see there is an omega to the d minus 2 here, and there is a 1 over omega that's coming from here. This is basically m over omega. Okay, so that gives you omega to the d minus 4 and m square. And now if you put the corresponding relation that omega is this, you get this to be m to the power d minus 2 by d minus 3 tau to the d minus 4. Okay, because for omega, I just put this value over here. So tau is a small parameter. But you see that for any small tau, we can make this large by taking m to be very large. Right? And that's what one would expect, right? If the external objects that are scattering are very highly massive objects, okay, relativistic and coming within the Schwarzschild radius of each other and scattering, we expect lots of gravitons coming out, right? Because that's a strong gravity of emission process. So classical limit then will correspond to large m. Yeah, d equal to 4, it doesn't depend on tau. Okay, it's for the formula is simpler, d equal to 4. But d equal to 4, as I said, there are infrared divergences, right? And they affect also the classical limit. If I have time, I'll discuss at the end. It's not unsurmountable, but I think it's a more complicated problem. Okay, one has to understand better what to do in d equal to 4. The leading theorem has no problem. Okay, that can be applied even in d equal to 4. In fact, it was used by a long time ago. Okay, to do classical scattering. Okay, yeah. So those you are also always thinking of as small but fixed number, right? Exactly, that's right. Okay, so that even so you fix your bin, right? In a given bin, that means in a given angular range and a given fractional range in energy, you can make the number of soft gravitons to be very large if you make m very large. Right? The fact that a depends on these is not surprising, right? Because if you fix all your parameters and start reducing the bin size, right, then obviously less number of gravitons will be emitted in that bin, right? Because you are allowing less phase space. Right? So that's the dependence on delta and omega. So this is quite, somewhat trivial dependence. So you have to always think of delta and omega being small but kept fixed, and then you are taking m to be large. So classical limit corresponds to m goes to infinity. Okay, but there is something else that you have to ensure. And that is that while we do want that there should be lots of soft gravitons emitted, okay, in order for the classical formula to make sense, we don't want this number to be too large. And the precise statement is that we don't want the total energy that is carried away by the soft gravitons to be comparable to the energies of the external particles, okay, which are of order m. So total energy that is carried away by the soft particles should be small compared to m. And the reason for this is the following. As I have been emphasizing, the soft formula, the S0 factor, okay, which is here, you see that this contains sum over finite energy states, okay, which in a given problem will take to be the external objects which are coming in and which are going out. But in principle, one should include in this sum also the contribution from the other soft gravitons, right? In a given process, take a particular soft graviton, okay, that has a soft factor. Okay. We have taken into account the possibility that corresponding soft factor gets contribution from the sum of particles which are finite energy. But what about the sum of particles which are soft particles? Okay, what about their contribution? I had argued earlier that this is encoded in m. Okay, But okay, we'll come back to M, but on physics ground, we can see that if it so happens that the total energy that is carried out by all these soft particles is comparable to the masses of the hard particles, then their contribution to this factor would become comparable to the contribution from the finite energy particles. Is this one clear? You see that this contribution, let's just do a simple estimate. This goes as E over omega. Okay, where E is like Pi goes as E, right? That's of order M, okay, over omega. Now, suppose there is a soft particle. Okay, what would we expect for that, for its contribution? It will be the energy of that soft particle over omega. So that's negligible, right? The energy of a soft particle is very low. But if there are lots of soft particles, you have to add up their contribution, right? So total contribution to this formula from all the soft particles that are emitted, so the total energy of the soft particles divided by omega. So if the total energy carried by the soft particles becomes of order of the masses, right? Then we are making a mistake in using this as a soft formula. In other words, this assumption that the emission of the soft particles are independent no longer holds, right? The emission of one soft particle depends on the on how much of the other soft particles have been emitted. So this is a reason, okay. So this is a technical point. Okay. There may be with some clever arguments one may be able to do better. Okay, you have to modify the formula. Okay. But if we just want a simple-minded application of this formula, okay, where you use this product of S0, okay, then we have to impose this constraint. Okay, the total energy carried away by the soft particles should be small compared to M. No, everywhere, in all bins. Because in general, a soft particle in a given bin can get contribution from soft particles in all bins. Right? So it's really the total energy carried out by some of the soft particles. So let's try to make an estimate of this. You see, I have already given the expression for total energy in this bin. Okay, that's here. So S0 we saw is of order M over omega. So suppose omega has an upper cutoff. Suppose which I'll parameterize as sigma times A inverse, because A inverse is a natural length scale, right? Everything is being done in terms of A inverse. So let's call this sigma times A inverse. So sigma is some parameter. We'll see what constraint we will have on sigma. Sigma is some parameter. Then an estimate of the total energy that is carried away by the soft particles can be obtained by simply setting omega to be sigma A inverse in this formula and taking this omega, okay, now this instead of a small solid angle you integrate over the whole solid angle, so it becomes of order 1 number. Delta you allow a range of order 1, right? So that's basically you don't use a small range, but you just say use the whole range from up to the cutoff. So you just substitute omega, if you just replace omega by that cutoff in this formula, okay, that's a rough estimate of how much energy is radiated away, total energy. So then total energy radiated, total just 1 minute. Let me write this formula, then I'll come back, is A omega at omega of order sigma A inverse. Yes, what is the question? See, in any given situation, there is always an upper cutoff. If we consider the case when the two black holes come close and scatter, okay, there the upper cutoff will be of the order of the inverse partial radius, right? Because we expect that the typical gravity waves that will be coming out will have frequency of the order of A inverse okay, and beyond that, you don't expect gravity waves with wavelength that is much smaller than that, right? Because that's the typical length scale of scattering. Okay? So in any given physical situation, we can choose the cutoff, and we will consider various examples. Okay? So it's basically the inverse of the typical length scale that is involved in the problem. Okay, so this can be estimated. So here you see it was m square omega to the d minus 4, right? So at omega equal to sigma A inverse is, I use that formula over there, or I can use from here, A, let's use this formula, m square omega to the d minus 4. So that's m square omega to the d minus 4 times omega, that is m square omega to the d minus 3 at omega equal to sigma times A inverse. So this is m square sigma to the d minus 3 and A to the power minus d minus 3, but this is nothing but 1 over m. Right? That's the relation between the Schwarzschild radius and the mass. A to the d minus 3 is of order m. So this gives you m times sigma to the d minus 3. Yeah, so when you are talking about the cutoff, right, then tau is of order 1, because you have to put basically, yeah, tau, you have put tau equal to sigma, right? Tau was the soft parameter, right? You want to make keep tau small, but now you are saying that let's just use this formula all the way up to the cutoff. Okay? You will of course make some mistake when tau is close to the cutoff, right? Because this formula is not strictly valid. But as far as the order of magnitude estimate is concerned, you can just set tau equal to the cutoff, okay, and then calculate this. So that corresponds to setting tau equal to sigma. Right? That's all we are doing. Okay, but this again up to numerical factors, right? We don't expect this in an exact formula. Okay, but as far as the order of magnitude is concerned, this is what we get. Is this clear? Is this calculation clear? So let me repeat again what we did. We calculated using the soft formula, we calculated the number of soft gravitons in a given bin. We multiply this by omega to calculate the energy carried by the soft gravitons in a given bin. Now you want to estimate the total energy carried by all soft gravitons in all bins. And we said that the way we estimate it is by setting omega to be equal to the cutoff. And we set the angular width, angular range omega, the capital omega, to be 4 pi in 4 dimensions. In higher dimensions, it's some powers of 2 and some power of pi. That's the number of order 1. And also we set delta to be of order 1, right? Because we are not interested in the range where omega is in a small range. We really want omega to go all the way to the cutoff, starting from 0. Yes. No, it's not. We'll see. We have right now we have not said anything about what sigma is. Now we have to see under what condition we can make this small. Yes, I think that there is a power missing somewhere. Let me just fix that power. I think this tau, what did I, yeah, okay, yeah, this is fine, I think, yes. Pardon? Yes, d equal to 3. Well, d is never equal to 3, it's equal to 4. Pardon? See, d equal to 3, there is no graviton, so it's not even clear what you are asking, right? Because this question of soft theorem makes sense only from d equal to 4 onwards, right? As I said, d equal to 4 has infrared divergences. Leading is okay, but once you go beyond leading, there are infrared divergences, so you cannot really talk about soft theorem, at least in the current form, in D equal to 4. Okay, but again, as I said, that I think it is possible to repair it, but you have to take into account the infrared effects more carefully in D equal to 4. Not in gravity, I think. Right? Because these are, yeah, I don't think, because, okay, first of all, you are not talking about very high energy scattering. Right? Sudhakar form factor comes when there is a massless, either massless particle scattering or a very high energy particle scattering. Here you are talking about massive particles which are carrying energies of order 1, okay, or of the order of the masses, right? So in that limit there is no Sudhakar suppression, right? Sudhakar suppression comes when at a very high energy scattering, right? So you are not talking about that regime here. And the point is, I mean, in gravity, Sudhakar, okay, one origin of Sudhakar form factor is the collinear divergence. Right? In gravity, there is no collinear divergence. Right? So that's another way of saying, while even for massless particles, there will really be no Sudhakar form factor in the standard form. Okay, so we see from here this formula that if we want this to be small compared to m, because that's what we demand, right? Total energy radiated should remain small compared to the mass of the individual object, right? Because that's the order of the energies of the individual objects. We need sigma less than 1. We need sigma to be small compared to 1. Otherwise, the effect of soft particles on the soft factor cannot be ignored. Again, in principle, it may be possible to take into account those effects, okay, but you have to use a more complicated formula. Either at the level of the formula that you have used, we need sigma to be small compared to 1. So now the question is, how can we make sigma small compared to 1? How to make sigma small compared to 1? Well, in a given problem, sigma is fixed, right? That's the frequency gets cut off at some point, right? So the question is, how can you make the cutoff? So basically, what you have to do is that make that cutoff not the inverse of the Schwarzschild radius. Okay, that's the natural cutoff, but you have to make it smaller than that. Okay, so effectively, what you are saying is that the length scale, in terms of length scale, the typical length scale that controls soft radiation should not be the Schwarzschild radius, but something larger than the Schwarzschild radius. Okay, because then its inverse will be small compared to the inverse of the Schwarzschild radius. Okay. So how do you keep the typical length scale to be large compared to the Schwarzschild radius? So there is one simple way to do this. And this is to keep the impact parameter large. Keep impact parameter large compared to the Schwarzschild radius. Because if you keep the impact parameter large compared to the Schwarzschild radius, okay, then for relativistic collisions like this, the typical length scale will be the impact parameter, not the Schwarzschild radius, because that's the closest distance of approach between the two objects. And in that limit, you can try to ensure, in that limit you can ensure that the sigma, effective sigma, is the inverse of the impact parameter, and or the, yeah. So this cutoff, sigma A inverse will be like B inverse, okay, where B is the impact parameter, and that means sigma is small. Okay, maybe I write that formula here. If B is impact parameter, then cutoff is of order B inverse. So now we parameterize the cutoff by sigma A inverse. So we equate sigma A inverse to B inverse. So sigma is A over B, which is small. Okay, for large B. But this is perhaps not that interesting because you have to really, we cannot let the black holes go close to each other, right? You have to keep them far away, just to make sure the total energy radiated is not of the same order as the masses of the black holes. So I'll consider now another limit, okay, which also achieves this, where the two black holes or two particles, two objects that we have can come close to each other, but one of the objects have to have mass that is small compared to the other object. Okay, this is what we call the probe limit. You take 2 to 2 scattering. With the following kinematics. Okay, so let's take P1, the first particle. So this, I'm putting them in a bracket, just not confuse them with the various components, the space-time components. So P1 is P1 0. P1, P2 is P2 0, P2, P3 is M 0. Okay, this is the heavy object, and we are working in a frame where the heavy object is initially at rest. And P4 is minus M minus P1 0 minus P2 0 and minus P1 minus P2. Okay, and they satisfy appropriate on-shell condition. I am not even assuming that these two particles have the same mass. Okay, so P1 0 square is equal to P1 vector square plus M1 square, etc. Okay, so this is a very general scattering, right? One light object scattering from a one heavy object, okay? And in that process, it may even happen that some part of the light object gets removed from it and gets absorbed by the heavy object. Okay, so we are not assuming that the masses remain the same. Okay, a general scattering. The only assumption is that the light object is light compared to the heavy object. Okay, the M is large compared to the M1 and M2, the small M1, M2, etc. You can also consider merger, in which case this will not be there. Okay, that also you can consider. That's a special case of this. I'll write down the formula and then you just have to remove this to consider merger. Okay, objects colliding and becoming another object.
You require that.
Yes.
You require that mass you want.
Not.
I'm sorry. I mean, the mass is the same before and after this.
No, because that's why M1 and M2 can be different. That's what I said. That for P1 the mass is M1, for P2 the mass can be M2, right? Because during the scattering, some mass can be absorbed by the heavy object, right? Or it may even collide and nothing may come out. One of the ingoing particle. Capital M is the mass of an ingoing particle. Okay, our convention is the momentum is positive ingoing. So capital M is the mass of one of the ingoing object, okay, which I have taken to be at rest. I am working in the rest frame of that object. Are equal. No, nothing is equal. Oh, the ones which are positive energy, these are ingoing. P1 and P3 are ingoing, and P2 and P4 are outgoing, right? So what is ingoing, what is outgoing is decided by whether the energy is positive or negative. Oh, sorry, I think, okay, this P2 naught will have to be negative. Okay, so let me maybe say that P1 naught is positive and P2 naught is negative. Okay, for this it's clear. Okay, P3 is ingoing, P4 is outgoing. For astrophysics, okay, here we are thinking of this as a scattering object. Okay. If you think of the collapse of a binary system, okay, that's different from this one. Okay. Because that's not really a scattering problem, right? It's one object, so it's like one object decaying into some gravity wave plus some residual object. Okay. So for that object, if you want to apply soft theorem, right, there the soft emission, the soft factor will basically come from all the gravity wave that is being radiated in that process. Okay. So I mean, there you really have to know what finite energy gravity waves are emitted, and based on that you can calculate what the soft gravitons are. Okay. Here we are trying to make an approximation where we can forget about the contribution from the contribution to the soft factor from the soft gravitons which are being emitted. Okay. But there that's the only contribution, right? So the soft contribution will basically come from the final state outgoing gravitons. That if we consider the collapse of the binary system, right? Whether this applies there, right? So the way I have set up the problem, this is really two particles actually colliding, okay, having velocity of order 1, and then either they can merge, in which case this is absent, right? Or they just scattered. Okay? But we will not assume anything about the impact parameter being small. Okay, it can be as impact parameter being large. It can be as small as the Schwarzschild radius. Okay, so close encounter, okay. But you have to keep these masses small compared to the large m. Okay, we will see why that helps. Okay, right now there is no justification, right? Okay, I can make this assumption, of course, I can make this configuration, but the fact that it actually keeps the total amount of radiation small, we have not shown, right? That's what you have to check. Yes. But this requires only the initial and the final state, right? So they may be deformed during the collision, right? But calculating the soft factor requires only the initial state and the final state. Okay? State far before the scattering and state far after the scattering, right? So by that time, it has become normal black hole with a spherical event horizon, right? Or even rotating black hole. Okay, so because you can see this formula doesn't, the S0 doesn't even know about the angular momentum, right? S1 cares about the angular momentum, but that's the only thing it cares about. Okay? If it was not black hole but a neutron star, right, and it got some permanently deformed during the scattering, it doesn't matter, you can still apply the same formula. Okay, now I'll give an exercise. This I'll not prove. As m becomes large, okay, so take m goes to infinity, S0 takes the following form. It's written as a sum over only the light states So this you recognize. This is the usual soft factor for the particles 1 and 2. These look unfamiliar. Okay, these are not there before. Okay. But what was there before is the contribution to the soft factor. Maybe I should have. No, I think the labeling is correct. What was there before is the contribution to the soft factor from particles 3 and 4, the heavy particles. Right? Because to begin with, these should have had contribution from all 4 particles, right? Light particles and heavy particles. What you can show is that in the limit when the mass of the heavy particle goes to infinity, the effect of the heavy particle soft factor can be rewritten in this form. Okay, this is the exercise. Okay, it's just straightforward algebra. Okay, and so we'll work with this factor now. In S0 is of order m over omega. It's easy to check. Okay, these factors are all, of course, m over omega because it's like m square over m omega, right? M over omega. These also you can check. It's like m over omega, right? One factor of k cancels this. This is also m over omega. Okay, so all terms here are of order m over omega. So S0 is of order m over omega. But the cutoff on the frequency this is of order A inverse, where A is the Schwarzschild radius of the heavy particle. We cannot let the light particle come at a distance that is less than the Schwarzschild radius of the heavy particle, right? Because then it will just be absorbed. Then nothing will come out. So it's a different problem. So whether it's absorbed or whether it's scattered, okay, the cutoff is of order A inverse. And it's a simple exercise from here to check that after you put, so this is A inverse and A is of order m, so that's m inverse. No, m, not m inverse, m to the power minus 1 over d minus 3. A omega at omega equal to m to the power minus 1 over d minus 3. Okay, let's use this to calculate this, okay, because this is the cutoff. This is of order m square over m. Just again, straightforward algebra. So what has happened, okay, is the following. See, earlier you are getting something of order m, right? If things are coming within Schwarzschild radius. Here, what has happened is that the S0 is sensitive to the mass of the light particle, m over omega. But the cutoff on omega involves a heavy particle. If this was small m to the minus 1 over d minus 3, okay, which is what was the case earlier, then you would have gotten something of order m. But because it's capital M over here, you get a factor of small m square over capital M. Okay, it's just algebra. You use this expression for A, use this estimate for S0, which is given here, and you will find this. And this, of course, is much, much less than m. So this is the second way, okay, which is perhaps a more interesting way of keeping the total amount of radiation, soft radiation, small compared to the masses of the objects that are scattering, okay, even the masses of the light objects. Yes. Yeah, say for example, if the planet mass is small compared to the black hole mass, then this formula holds. No, it doesn't have to be. You have not really assumed anywhere it's black hole, right? I'm just using this estimate that, I mean, this can be changed a little bit, right? I'm using this notion of a black hole because you are using this A inverse as a cutoff, right? That's all. If if it's not a black hole, then the cutoff is not exactly A inverse, but some multiple of A inverse, for example, right? Yeah. Yes. Well, the point is you have to make sure that the total amount of energy radiated is large, right? If you throw too light an object into the sun, right, then the classical approximation itself may not hold, right? For the classical approximation to hold, you have argued that the total amount of gravitons that are radiated should be large, right? And that we have seen that requires that the masses should be large, right? Here, for example, this is the total amount of energy that is radiated, right? You can calculate from here the total amount of gravitons that are radiated. Right? If this is too small, okay, then you will find that the number of gravitons radiated is not large enough. So even the classical approximation breaks down. Yes. Yeah, exactly. Right? So you can work out what that mass will be. So what we need, maybe I should have said this, that we need this to be small compared to m, but we also need this to be large. Okay? The number of gravitons emitted should be large. Okay? The total energy that is carried by the gravitons should be large. Okay, so now let's go to the subleading order. So in the subleading order, okay, you remember that S1 had a factor. S1 had this combination: pi mu del pi rho minus pi rho del pi mu. Okay, there is a factor like this inside in the expression for S1. And these derivatives are the problematic ones, because that's the reason why S0 and S1 didn't commute. But in the classical limit, okay, when it acts on a wave function, which is like a classical wave function, classical limit, del pi is basically I times x. Right? That's the representation of x in the momentum space. So this basically, once you work out the fact that this becomes I times xi rho pi nu minus xi nu pi rho, xi pi nu, which is nothing but I times j orbital mu rho mu. Okay, this is just a standard classical angular momentum of the particle. And the soft theorem, the S1 also had a spin part. Okay, so we can add up the spin part, okay, and using that we can write down a neat formula for S1, and that's this. So S1 can be written as I times sum over, say, A equal to 1 to n, if there are n external particles, let's say capital N, epsilon mu nu E A mu A rho over E A dot A, and J A rho nu, where this is just the classical angular momentum. No, because this contains both the orbital and the spin part. See, the spin part are also there, right? Plus there is a plus a spin part, right? This one, we saw that it's I times the orbital angular momentum. The spin part just basically becomes I times the spin angular momentum. Okay. So in the classical limit, this becomes the total angular momentum, okay, which includes the orbital and the spin. Plus spin. Okay, but these are classical orbital and classical spin angular momentum. Yes, exactly. Yeah. So if the black hole is rotating, then there will be a spin contribution, or black hole or anything, the scattering object. If that is rotating, then there will be a spin contribution to the soft theorem. But now you see that the problem that we are facing earlier, that S0 and S1 do not commute, doesn't exist anymore, right? Because this is classical, okay, just multiplicative factor. Is that clear? This is just, this object, right, is a purely classical property of the external object, right? S0 was also a classical factor, calculated in terms of the orbital angular momentum and the spin angular momentum of the object. So now, in principle, we could have written down a formula that we wrote down earlier, okay, the naive guess. Okay, so let me remind you what that formula was. So remember that a naive guess was that we have a product like this. Okay, but this was not working because this formula is not even invariant under the exchanges, right? It depends on in which order you take this product. That problem at least doesn't exist here, right? Because these are just commuting multiplicative objects, okay, calculated in terms of classical properties of the objects which are scattering. Nevertheless, you may ask that we had this factor of m, right? I mean, we said at that time that this naive guess is not working, and then we went ahead and calculated it explicitly. We found some terms which are like this, products, but then there are also some correction term, that is the contact term, m. So you can ask, what about that m, right? I mean, we had calculated it after all, right? So where did it go? And what you can show by doing this careful analysis is indeed that in the classical limit that we are taking, that m actually goes to 0. And it is not too surprising. And the reason that it's not too surprising is because we said that one of the effects of m is to represent the contribution to the soft factor due to the soft particles, right? That once a bunch of soft particles is emitted, then one particular soft graviton can, the soft factor for one particular soft graviton can get contribution not only from sum over the finite energy states, well, I don't have that formula anymore, there is a sum over A, well here, sum over A here. You should also include contribution from the other soft particles that are emitted. But under the condition that you are working, where the other soft particles that are emitted don't carry too much energy and also too much angular momentum, their total contribution to the soft factor can be ignored. And that is basically represented by m. So the fact that the effect of m goes away in the classical limit is correlated with the particular limit that we are taking, where the total contribution to the emitted energy from the soft particles remains small compared to the finite energy particles which are being scattered. Is this statement clear? So there are two statements which can be checked independently, that the effect of m is small and that the total energy that is carried out by the soft particles is small compared to the energies of the external particles. This is also true for angular momentum. But what I am saying now is that these two are not independent facts, they are related, because m actually represents that effect, okay, the effect of the soft correction to the soft factor due to the soft particles. Yes, you had a question? M. Oh, that capital, this m. This m that we introduced, yeah. Or we call it capital M, right? Yeah. Yes, of course. But once you put those values in, right, for the particular configuration that you are working in, you will find that the effect of this is small compared to the product of the S's, S1, S0, S1 product. So this requires some work, just scaling, right, not too much work. You just have to see how this scales compared to this. Exactly, the order of magnitude analysis will tell you that the effect of this is small compared to what you have included here. And that, as I said, is related to the fact that the total energy that is carried out by the soft gravitons, we have kept small compared to the energies of the individual particles. So this formula then is indeed the correct formula. And now all you have done earlier can be done with this formula. All you have to do is that the S0 has to be replaced by S0 plus S1. So in this formula, this S0 now will be replaced by S0 plus S1. This gives the subleading contribution to the number of soft gravitons that are emitted in a given beam. Is this point clear? Okay, then once you have this product structure, right, then the same argument that gave this formula will now give this formula, okay, with S0 replaced by S0 plus S1. Okay. And in fact, what one can show with some more work, that it also goes up subleading order. It gives you S0 plus S1 plus S2. Yeah, so they are independent events as long as the total energy that they carry away is not comparable to the masses of the external particles. Because in that limit, right, the most of the contribution to the soft emission comes from independent emission of the soft particles from the external legs, right? Is that the probability that a soft particle is emitted from the external leg is much higher than that they will be emitted from one of the internal legs. That's what it represents. Not internal legs, one of the soft particles, right? There are external hard particles and then there are external soft particles. The probability that they will be emitted from the external soft particles becomes small compared to the probability that will be emitted from external hard particles. Okay, that's the physics. So let me then summarize by saying what this formula is giving us, right? What is it achieving? What it is telling us is the following. So let's suppose that you have a scattering. Okay, either in the probe limit where a light particle scatters of a heavy particle going close to the heavy particle within Schwarzschild radius, or in the other limit where we keep the impact parameter to be large, okay, masses are of the same order. In either of these cases, suppose we know the initial particles, okay, initial particle trajectories and the final particle trajectories, and the initial angular momentum and the final angular momentum, the spins. Then you can calculate S0, S1 and at least the universal part of S2, just in terms of the angular momentum. Is that clear? Okay, the particle trajectory will tell you what the angular momentum is, right? Maybe I can write down that formula also. Well, I am a bit past the time, but let me just say this. So if the eighth particle trajectory, if eighth trajectory is x mu a equal to c a mu plus say p a mu over m times tau a. Okay, this is the velocity, the core velocity or the d velocity, okay, multiplied by the proper time. These are some constants. Then the orbital angular momentum j mu nu, the orbital part, is just c a mu p a nu minus c a nu p a mu. Okay, you can substitute x, but of course the p part cancels, right, because of this antisymmetrization. So it's this. So if you know the initial trajectories, you can calculate the orbital part. Okay, initial and the final trajectories. You can calculate the orbital angular momentum, spin angular momentum, of course, is measured, how much spin was there in the particle. So you know all the terms that are needed to calculate S0, S1 and S2, the universal part of S2, okay, which involves the JJ contribution. Just knowing that, without knowing anything about what happens inside. Inside, there may be an explosion, okay? There may be electromagnetic interaction, there may be some other interaction that you don't know of. Doesn't matter, you know the initial incoming trajectories and outgoing trajectories. Based on that information, you can predict what kind of soft graviton radiation will come out, up to subleading order without any restriction. At the sub-subleading order, you can do it only in the situation where the universal part dominates over the non-universal part. Okay, so that's basically the content of the classical version of soft theorem. And this can in fact be tested in many examples. Okay, there are simple examples that you can cook up where you can actually consider this kind of scattering and calculate explicitly how much radiation is coming out. And you can check in those simple cases that the result is perfectly consistent with what the soft theorem is giving, okay, up to sub-subleading order. In 4D, as I said, because of the infrared divergence, okay, see in 4D, one of the problems you can easily see that, I mean, this formula itself that I have written, okay, actually is not valid in 4D. Okay, because of this long range gravitational force, okay, there will be logarithmic term here. And because of the logarithmic term, when you calculate J mu nu orbital, it will be this plus a term that grows logarithmically with time. So it's not even clear what this formula means, right? That basically is a reflection of the fact that this small omega expansion that the soft theorem is giving is breaking down at the subleading order. That it's not 1 over omega plus order 1 plus it's 1 over omega plus log omega. So it is in principle possible that by being very careful, we can actually extract the coefficient of the log omega piece. But then you have to modify the usual soft expansion. It's not the usual soft expansion anymore. Yes. Yes, in the classical limit, there is really not much distinction between fermions and bosons. Suppose you have a very heavy object, right, and which is bosonic, and you add an electron to it, right? It really makes no difference. The soft particles are, of course, bosonic here, right? It's gravitons which are being emitted, right? But the hard particles, the finite energy particles, whether they are fermionic or bosonic, doesn't really make any difference in this analysis. Because soft theorem is valid for both fermionic and bosonic external particles. Okay, I think I'm done. Yes. How to solve IR divergences? Okay. Okay, there are two ways of addressing IR divergences. Both makes use of soft theorem, but of course it's not directly, I mean, you have to do more work besides soft theorem, right? One is that you look at cross section. The idea of looking at the inclusive cross section is that you calculate scattering, but instead of looking at scattering into a given final state, you ask for scattering into a given final state plus arbitrary number of soft photons that are being emitted. So in that way of looking at it, the way soft theorem helps is that it tells us what is the scattering cross section for an amplitude with arbitrary number of soft gravitons or soft photons emitted in the final state. So that information comes from soft theorem, and then you have to do some more loop calculation to show that that cancels against the usual IR divergences that appear in the loop. Okay, so that's one way of addressing infrared divergences. Other way is to try to define J states, and again in that J state formalism, right, you need this particular understanding, okay, of what the soft graviton amplitude is to see what kind of bracing you need to cancel the IR divergences. Okay, so this is basically used as some technical information that goes into showing that there is a cancellation of divergences, right? When you trace the states appropriately, you can cancel the divergences that appear in the usual S matrix. So let me emphasize again, the soft theorem by itself doesn't solve IR divergence, but the results of soft theorem are used in the process of showing the cancellation of higher divergences in 4D. By dropping the.
Can you show the conservation of angular momentum at the subleading level? Because that was also needed for maintaining gauge invariance.
The M term.
Yeah, I mean capital M term at the subleading.
We are not dropping it. Okay, maybe I should have said that. Just like S0 got some contribution, right? Let me write down the expression for S1, which I had meant to write down, but I didn't write down. So we parameterize the angular momentum. Of the light particles, we call, say, J1 mu nu, J2 mu nu. Okay, these are the two light particles. Okay, then for J3 mu nu, I take the following form. Okay. So J3 0I, I take 0, and J3 ij, these are the space components. This I take some Jij. Okay. So this means that we are now measuring the angular momentum by choosing the origin of the space-time coordinate or the origin of the space coordinate as where the heavy particle was there initially. Okay, this is the initial state of the heavy particle, right? That's why the 0I component is 0. So I fix the origin of the coordinate system, and then J4 ij or J4 mu nu by construction is minus J1 mu nu minus J2 mu nu minus J3 mu nu. Okay, so you angular momentum is manifestly constant. Okay, J is the total angular momentum, orbital plus spin. Now what happens is that if you calculate the soft factor S1, so this is in the probe limit. So this is probe limit, okay? M goes to infinity limit. If you take the M goes to infinity limit of the original S1, right, which had contribution from 1, 2, 3, 4. Okay. This is the contribution from 1, 2, the original contribution from 1, 2. All of these that you see are contributions from the 3, 4 particle. Right. So these are the contributions from the heavy particle. You have taken its mass to infinity, but it doesn't go away. Okay. It leaves behind some contribution which is expressible in terms of the angular momentum and the various properties of the original objects. Okay. So angular momentum conservation we have imposed explicitly, so angular momentum doesn't go away anywhere, okay, and this is necessary, and once you impose this constraint, this is the formula you get. The reason that the contribution from the heavy particle involves the angular momentum of the light particles, it may look surprising, but the reason that it's not surprising is because J4, which is the heavy particle, actually is sensitive to the angular momentum of the light particle, right? We are explicitly imposing momentum conservation, angular momentum conservation.
In your study, you take the relativistic limit for the black hole, right? So
well, relativistic, it's not a limit. You are thinking of the velocities of the order of the velocity of light.
Right. But in my naive expectation, in the realistic case, the speed of black hole when they interact is much slower than the speed of light.
That's true, yes.
You study the non-relativistic limit?
Well, in principle you can, okay. We have not tried to do this because, I mean, for the realistic case, we should really go to 4 dimensions. Right? So I think the first thing to do is to try to understand how to go to 4 dimensions. And then you can try to take the non-relativistic limit of that formula. Right? Because in 4 dimensions already, even for relativistic scattering, there is an issue about the infrared divergences. Right? So I think if you want to go actually say, for example, what happens when there is a merger, okay, 2 black holes which are coming with a small velocity with respect to each other and merge. Okay. We can try to study this problem by using the same principles, okay. But first we have to understand the infrared divergence issues, okay, and then we can try to take the non-relativistic limit.
Can I ask another question? So when you consider the multi-graviton soft limit, is there an issue about taking the order of the soft limit?
Taking the
order of the soft limit for different gravitons, or just making symmetric to sum over all the...
Well, the point is that in the classical limit, right, this is the formula, this product formula. When why you are taking the multi-graviton, right, is because the multi-graviton is the right thing to do because there will be lots of gravitons emitted in the classical limit, right. So a single graviton emission is not going to be very relevant, right. In any bin, in the classical limit, we expect that the peak distribution will involve lots of soft gravitons coming out in that bin, right. So that's why the correct starting point is the multi-graviton soft theorem, right, not single graviton soft theorem. But in the classical limit, okay, there is a simplification that it becomes a product of single gravitons, okay. That requires 2 conditions. One is the classical limit, and the other one is that the total amount of soft radiation remains small compared to the energies of the individual objects. Okay, under this condition, okay, you have a factorization that the multi-graviton soft limit is a product of the single graviton soft limits, okay, and you get a simple formula like this. Okay. If you want to go beyond this, right, you have to try to see how to modify this. Okay, you don't have the simple product formula anymore in that case, right, but you can try to see whether you can systematically correct, for example. When the energies become of the order of the external masses, okay, then you have to take into account the effect of the soft gravitons on the soft factor. Okay. In principle, you can try to do it systematically, okay, to see if you can find corrections. But this is the leading formula, right, in this limit.
Thanks.